Okay, so we're going to get started here on Module 6. You'll notice that Module 6 covers both belt and chain drives. In our book, it's going to be Chapter 11, and it does cover both of them. The first part of the chapter is dedicated to belts. The second part of the chapter is dedicated to chains. We're going to find a lot of similarities here in relationships to what we had learned from gears, okay? But there's some nuances about how they're different and, types of applications that they would be on, which would so we'll talk about that. As we look at our learning plan, you're going to notice here that I have a Chapter 11 PowerPoint presentation. We'll be pulling that up to kind of walk us through the sections in Chapter 11 that we're going to be looking at. Then you'll also notice there is a place for session recordings. I will be recording, obviously, this and posting that later on. If you look out there, there are the recordings from previous courses. So if you did want to look ahead or such, those are out there for you. And then just like we normally do, we're going to have some practice problems and an assignment. So the practice problems are going to be out of our chapter. It's going to be examples 1 and 2 and 3. Both examples 1 and 2 we're going to be doing today, and those are going to be specifically for the belt drives. And then example 11.3 is going to pertain to chain drive. The last items that you have here is make sure that you identify a couple things that you learned here in Module 5. And then I would like you to describe one of each, name and describe an application, one for belt drives that you come across in your everyday life, and then one for a chain drive. The only thing you can't use for this application is a bike, okay? Because I'm pretty sure everybody is familiar with a bike. I want you to go beyond that, okay? And just kind of look around and see where you see an application of each one of these. And once we get to know them a little bit more, it'll make more sense. Then your assignment number 6 is going to be problems from the end of the chapter. And again, they're going to be pertaining to both belt and chain drives. And once we're done with our lecture, you'll be able to, have a good idea of how to do those. So I'm gonna go back up to our learning plan. I am going to open up our PowerPoint presentation, and Chapter 11 starts on page 302. So if you want to open up your book to page 302, that's where we're going to kind of get started here. So the objectives of this chapter are really going to be to look specifically at the beginning of the design phases pertaining to belt and chain drives, okay? And then using catalog information, or really out of our book, out of standard tables, we're going to be specifying the actual belt and chain drives that we would use for an application, okay? We're also going to look at the relationships for both belt and chain drives, and we're going to, again, see some similarities that to what we had learned from gears, okay? So that'll be kind of fun to see those. In the introduction here, they're going to kind of talk about and differentiate belt and chain drives as they differentiate from gear drives. So for instance, belt and chain drives are going to be used to transmit power between rotating shafts. Now, that's a similarity to gears, okay? So gears were on rotating shafts, and we were basically transmitting that rotation from one shaft to another, but we had the purpose of usually slowing things down so that we could increase the torque and do more work. We're going to find that that's a common theme here with belt and chain drives as well. Belt and chain drives offer the flexibility of efficient operation at large and small center distances. The one big difference between gears and then belts and chain drives is that we now can take those center lines and we don't have to be engaged with teeth. I like to think of the center line between gears as being set, okay? When we have a belt and a chain drive, it's more flexible because now we can move that center distance for whatever size belt or chain that we have. So it becomes a lot more flexible. So if we do need center distances to be further apart than, items right up against each other like gears, belts and chain drives can be a good application for that. And then it says here, just kind of bouncing off of that, gears become impractical when the distance between the shafts become kind of large and spacious, So if we want to do that with gears, we got to gang gears together because they have to be, tooth to tooth engaged. Where with belts and chain drives, we would just separate them by a distance and we're good to go. Okay, we just get a longer belt or a chain. So let's talk about a bicycle chain drive. So a bicycle chain drive is going to be a chain mechanism that's going to transfer the motion and forces of your rotating pedal assembly, okay, where you're putting the work in, to what would be the rear wheel. Okay, I'm sure many of you have kind of looked down and experienced gears on a bike. Okay, that velocity ratio of the chain can be readily altered by relocating that chain with the levers that you have usually up by your handlebars, right? So you can kind of shift between the gears and then changing those velocity ratios because the size of the if you would gears that are there, when those physically change, now all of a sudden we're changing the gear ratio, and then also, you know, how we're able to perform. A lot of times, if you're going up or down hills, you want to change that gear ratio so it's easier to pedal. You might not be able to go as far as fast, but you're able to kind of keep going. Okay. On the other hand, when you're going, you know, down a hill or you're not, or you're on a, you know, kind of a flat grade, now you might want to increase that velocity ratio so that now what you can do is you can kind of go farther and faster with less pedaling speed. Now, belts and chains are commonly referred to as flexible connectors. Belts and chains and chain drive kinematics are exactly the same. Okay, so what's kind of nice is we learn the kinematics here at the beginning of the chapter for belts, and it's kind of like a ditto for the chain stuff. So that's why these are seen as being kind of ideal for being in the same chapter and together. In section 11.2, we're going to start specifically talking about and focusing on belts. So first of all, the function of a belt drive is going to be to transmit that rotational motion and torque from one shaft to another in a smooth, quiet, and inexpensive way. Okay, so first of all, belt drives are normally low cost, and they're low cost for a couple of reasons. Number one, the materials that are used to make them are readily available. The belts themselves are made with rubber and fibers and maybe even some metal that's infused on the inside, but it's very readily available. They also are going to be mass produced. If you go into any automotive store or even a hardware store, you're going to notice that there are belts, you know, usually hanging where belts are used in a lot of different applications. So they're going to be something you can just go up and pick up. So what I'm referring to are, you know, these belts like this. Now, belts are found on snowmobiles, motorcycles. They're on, you know, all sorts of drives. They can be in your appliances at home. A lot of machinery you're going to find are going to utilize belts. Our cars, automotive belts are there too. So so these are the types of belts that we're going to be discussing today. Go back over here. Oh, so they're low cost because they are readily available and mass produced. They also have flexible center distances. Like I said earlier, we can move those center distances to any place we really want them within reason, within the size of the belt, because we're not tied to having to be engaged with teeth. Okay, so so that is a huge advantage. Belt drives also operate smoothly and quietly. Okay, one of the reasons that we use belts, for instance, a serpentine belt in an automobile, is because they're quieter, okay, for this application. So when we have rubber up against metal, as opposed to metal up against metal, like gears, then we can hear the gears hit one another in some cases, not in all, but in some cases you can hear them operate. Chain drives, the same thing, but belts are nice and quiet. So we see them used in a number of applications for that reason. Another clear advantage they have over not only gears, but also chain drives is that you don't need any lubrication with them. Okay. Really, all the maintenance that you need is to look to see, is it kind of cracking? Is it seem like it's, you know, kind of wearing out? That's when you change them out. Okay. But we don't have any maintenance or lubrication that we have to worry about. They're also very easy to install and to assemble. Okay. And like I said, very little maintenance. And then they also have some stretchability about them. So they can take like an overload or a sudden shock without breaking or, you know, damaging other elements that are, you know, downstream, if you would, from those elements. So as we look at belts, we're going to notice on page 303 there is a nice illustration that shows us all the configurations of what we'll call the cross section of common different types of belts that we would consider for this application. So first of all, there's a flat belt. A flat belt truly uses surface friction to transmit usually motion and not much torque, as you can imagine, just because by its arrangement. But they are going to be designed to slip when they are overloaded. So, which isn't necessarily a bad thing. It protects then other elements downstream. The most popular is going to be the shape that we see here. This is a V-belt for those applications that I talked about earlier. Snowmobiles, motorcycles, all different types of appliance applications. And that's what this belt is here. Now, for those who are virtual, I realize this isn't going to be easy for you to see the cross section, but I'll pass this around in the room in a little while. But if we look at the cross section, we would see that it is shaped just like this, and that's why it's called a V belt. Okay. You can also have multiple V belts. I have one over here where the cross section, the grooves themselves, and again, I know online this might be a little bit harder to see, maybe through the light here, but this has multiple grooves in it. Oh, I'll go this way. Multiple grooves in it, so that now what we're getting is we are getting more surface area that we can transmit that rotational speed and torque as well. Okay. As you can imagine, you can create more torque, or you can transmit more torque because you have more surface area than that we're relying on to transmit. The next one that we have here is called a cogged belt. Now, in this case, the cogs, you'll notice that they take little like rounds out. This is not to engage with what we call a timing belt, which we're going to look at in just a bit. But what this does is this is a thicker, heavier, chunkier belt. And in order to make a radius, we need to take a little material away so that it can go around the like a smaller shiv. Okay. And then the last one we have is going to be a timing belt. A timing belt is still considered a belt, but it kind of operates a little bit more like a gear. So a timing belt, I have this one here. It's kind of large. Okay. You'll notice that it has these sections here. Okay. And what it does is it fits with a timing shiv, and I can kind of see I'm trying to do it underneath our camera here. But what it does is this actually fits down in. So now this is more like, if you would, a chain drive, because it has to line up and it's going to fit down into the grooves that fit the size of the belt that we have here. Okay. Now, for those who are in class, these are going to be available for you to kind of, peek at and look at. So I'm going to put those on the table in front here, and we can do it during our break or when we are in class. I'm going to put these too. I'm going to keep one up here. So really the kinematics part of it is going to be specifying what is the size appropriate for our application, because as you can imagine, there's different specifications and different physical sizes of the belts configurations as we see here. Go back underneath. So we kind of looked at each one of these. Oh, materials. You can notice here, I kind of mentioned earlier, we got rubberized fabric, rubberized cord, plastic, leather, fabric, just fabric itself. They can come in a lot of different configurations, and there's going to be pluses and minuses for each. So, so companies that sell belts are going to have their, if you would, kind of special way of application wise, which ones are gonna be best. So ones that are gonna have, cord in them, like steel cord in them, are gonna be, if you would, probably for longer life applications than ones that are just gonna be over fabric. Okay. So and that's where looking at a manufacturer's catalog and working through their process will help you to pick the most appropriate one for the application expectations that you have. Okay, so we looked at those. Now, shivs. Shivs are going to be sometimes referred to as pulleys that these belts are going to actually fit over the top of. So if I go underneath here, I'm going to zoom out, okay? And I know online this might be a little bit harder or virtual. This is our sheave, okay? And if we look at the side of the sheave or the cross section of the sheave is going to have this V shape for which a belt is going to fit down inside that cross section. So your sheave is going to be, if you would, is going to be a match to whatever the belt cross section that you end up choosing. So when we talk about a belt drive, it is going to be at least two pulleys, okay, or sheaves. Pulleys and sheaves are interchangeable when we talk about belt drives. So it's going to be two of these, and it's also going to be a belt that is going to fit over the top of those two sheaves, okay? If we peek ahead, when we look at down here, figure 11.5, this is going to be a straightforward drive. So you've got two sheaves or pulleys, and then you've got the belt fitting over the top. Once you specify the size of the cross section of that belt, the size of the two sheaves, what their center distance is going to be, and then how long does that belt need to be? That's going to be a full specification for a drive that you would use for a belt. So as we look here, figure 11.2, kind of bring this in here because I think I'll be able to be underneath here now. This would be kind of a nice picture of a cross section for what that pulley would look like, okay? So notice you have a hub, which we do on the one that I showed you earlier. You'll also notice that it has a bore with a keyway. That keyway ensures that whatever shaft it's mounted to, it's going to go at the same, or it's going to rotate at the same rotational speed. Then you're going to notice that this cross section right here is going to match up then with a standard cross section of a V-belt. And here are three of the most popular, okay? And we'll talk about that in a little bit. But that cross section has to match up with the groove, the V groove that is in the sheave. So that's why it's kind of like a match set, like I said earlier, okay? So you're going to be specifying the sheave or the pulley with the correct groove to accommodate the correct cross section for the belt. Now, as we look at the sheaves, as it says here, these are the wheels that are connected to the shafts that carry the belts. We just saw that. They're classified by their pitch diameter. Okay, so if we look back over here, you'll notice that there is a pitch diameter specified. Now, as you can see here, just like with gears, it's not a physical diameter we can touch. So it's not the outside of the sheave and it's not the bottom of the groove of the sheave, but it's kind of in between here. And as you can see, this is going to be just like it was for gears. It's like going to be where most of the carrying capability of the forces as well as that rotational speed occur, okay? And so we're going to be specifying pitch diameters for our sheaves. Also on table 11.1 on that very same page, these are the commercially available sheaves, okay? And why is that important? Well, that just means that these are off the shelf. So as we had looked at gears, there was tables for the diametral pitches of certain gears where these are going to be the standard size number of teeth on these gears in this, if you would, category or size tooth. Same thing here. When we classify the size of the belt, 3V, 5V, or 8V, and then physically looking, you know, they get bigger by the size, that we have to match the sheave to that cross section. And now these are the diameter, the pitch diameters of the sheaves in this category of belts. And then the same thing for the 5V and the 8V. Okay, so pitch diameter right here is that diameter, effective diameter, and these would be the standard pitch diameter sheaves for that size. Now, when you go out and let's say we find a manufacturer of belts that we want to work with or we want to specify for our design, they are going to have these three standard belts. But then what they're going to do is they're going to kind of expand on that, okay? And they're going to have probably more categories of belts that are going to have different types of characteristics that are going to then help you to specify them for maybe special applications that you might have. Okay. So belt manufacturers will have minimum these, but then they'll also have more beyond that to kind of differentiate themselves, if you would, in the industry so that they have more to offer. But just like for gears, and also if you even think of like hardware, like screws and fasteners, there's standards in that industry. There is here as well for belts. Here. As we look at figure 11.4, this is going to be how you specify the size of the belt. So if you recall from our gear design in our previous module, we had a chart where we would find, okay, how fast is the faster rotating gear and how much horsepower we have to push through there, which helped us to determine where we started with the size of the tooth or the diametral pitch of the gear that we were looking at. The same here is true for our belt drives. So you're going to notice here that we have a vertical axis, and this is going to be the RPM of the faster shaft. Okay, so this is going to be, if you would, kind of like a pinion in a set of gears. Okay, the faster of the two. And then you're going to notice we have a design horsepower. Okay. That horsepower is going to be, okay, how much horsepower are we anticipating transmitting through this application? And that's usually going to come from whatever your motor speed is or your input RPM generator. So that's going to be the horsepower along here. So what we're going to do is we're going to find out, okay, let's say we have an application, we've got 1160 RPM and we have a 20 horsepower application. So 1160 and 20 would come together right about there. Okay. You're going to notice that it is in the area that is specified as a 3V. Now, as you look here, you might be a little like, a 3V is the smallest size belt, okay? 5V is going to be that medium, and 8V is going to be there. Now, you as the designer, if you think you're a little bit close to an edge, it's never a bad idea to kind of move up a little bit just to get into the larger area, because then you're being a little bit more conservative with your design. So this would be, as a designer, you would, if you're right back in the middle, go with that belt size. But if you're on an edge, you usually want to then move up to the next size just for just making sure that it's a correct application and that you get more life out of that particular drive. Okay, so this is how you would try to, if you would, get in the ballpark. It's a starting point for your belt drive size that you would use. Always best to consult with and it says here, always best to consult with the actual manufacturer's catalog with for sizing. Now, those charts that we have here in our book are good, and they are for basic applications, especially in education, specifying things. But when you're out in industry, you're not going to pull out your kinematics book to specify shivs and belts, even though, yes, the sizes in here are standard. What you're going to do is you are going to open up the catalog of the manufacturer that you're going to use, and you're going to use their process step by step to specify the drive. Now, I'm going to ask you, why do you think that's true? Why do you think why do you think that's a good idea? And I'll open up our chat box for those who are virtual. Feel free to put in here or audibly let me know. Lars. Yep. Work in the vendor's world of available products. That's a good idea, because then you can ensure that you're getting something that's off the shelf and available. Okay, that's one good reason. What's another one? Because I said earlier, well, if I'm picking a 3V and they offer a 3V, why not just use the book information?
I think a good option might be like maybe their sizing and tolerancing is slightly different from company to
Could
company.
be.
Same thing with shoes.
Yes, you're right. Yeah, absolutely. No, that's a great point too. So when you're fitting it into your design, you want to be sure that you're using their application of what are the tolerances, what you can expect. Yep. I'm thinking a little bit further down the life of the belt drive. Let's say it's out in industry and we were expecting it to last, a good 3 years. And all of a sudden, within a month, that belt drive broke. Why would having consulted the manufacturer's catalog and following their process to size the actual drive be a benefit to us in that situation when something prematurely fails? Rainer.
I think maybe they're gonna give you, like a stronger, so they don't look bad with brakes.
Well, you're right, but even more importantly, let's say you specified and you didn't consult with them. You went to their catalog, the Browning catalog, you went through their process, you specified the belt drive, and it's breaking prematurely. What is something else that warranty? Yep, Aiden, warranty. That's exactly what I was looking for. If you follow their process and you document it and you're like, hey, this is what you said, or this is what your catalog says, it goes back on them for warranty and or liability. Okay. So if you have a situation where a belt broke and somebody got hurt and you are looking at getting sued, well, if that was a manufacturer's belt, if you would, a third party you incorporated into your design, and you did not follow their process, and you only were like, I think that one looks good based on, previous experience, and you didn't follow their process, you and or your company is going to be liable for that. And that could be, potentially a large lawsuit. Okay. So whenever you have manufacturers that you're working with and they have a process, you always want to go through exactly the process that they specify. When you're in your machine design elements class, Ryan is going to have you pull out catalogs that are actual manufacturer catalogs and kind of finish up these designs. And you're going to use their data and use their process so you get used to, kind of putting your nose into those catalogs. It's really important for those reasons. Warranty, but also liability potential down the road. Okay. All right. So always, if there is a manufacturing process and sizing, you want to make sure that you utilize their information and their way of sizing. Belt geometry. So we're going to be looking at, okay, the figure 11.5 down at the bottom of page 304. We did glance at this one already. Go back over here, but it is at the bottom of page 304. We've got this illustration. Here we have a typical belt drive. And again, we're going to have a smaller sheave. This would be the sheave that is going to be going at the larger speed. Consider this your pinion of like a gear drive, okay? And this is going to be where, for instance, on that same shaft, you're going to have your motor attached, okay? So this is going to be the input RPM. So it's going to be going faster. So our sheave is going to be a smaller diameter, okay? Then you're going to notice that it is going to have the belt wrap around, okay? And it's going to be down in the grooves of each one of those sheaves, and it's going to then rotate and transmit that rotational speed to a larger sheave, okay? So this would be like your output. Now, many times this is called driver, okay, and driven. Okay, driver and driven. They use the same numbering system for the faster as W1 or your angular speed 1, which is going to be the faster. And then the angular speed 2 is going to be the slower. One of the advantages, or I don't know the advantages, but one of the characteristics of a belt drive and the chain drive for that matter is whatever the direction of rotational speed is on your input, it's going to be the same direction of rotational speed on your output. Okay. If you recall for gears, when those were in mesh, it was always opposite, right? One to the other, just because of the nature of those teeth having to be engaged. Okay. So these are going to go in the same direction. And then lastly, once we specify how far they're apart they are, that's called our center distance, okay? This is where we talk about flexibility. So that center distance can be closer or further apart, as long as when they're closer, they're not interfering with each other. There are some limitations that belts are going to have, meaning there's going to be some radiuses, and this is where manufacturer's data is going to be really important. Like, what is the furthest apart we need the center line, or what's the closest that we can be? What's the smallest radius that we can have on a shiv for our belt to actually go around and have enough engagement, along that radius. So those are going to be specific to manufacturers, okay? And we can calculate what that, if you would, angle of wrap is going to be. But here's kind of the geometry of what we're going to be specifying, okay? Larger center distances. Oh, and then it says a normal center distance range is going to be as follows. So when we look at the second column here, you're going to notice that we have this relationship. So D2 is going to be the pitch diameter of the output shiv is going to be less than the center distance, but greater than 3 times adding the two together, okay? So this is going to be the range. So this is going to be the low end, and this is going to be the high end. And we have to make sure that our center distance lands in between those two numbers. So once we pick the diameters of the shivs of our drive, then we're going to be determining what is the appropriate center distance and getting that range between this number and this number, low and high value, and making sure that our center distance lands in between those two numbers. Okay. Okay, we looked at the sketch of the belt drive geometry. Another thing that we need to specify in our belt drive is going to be how long the belt is. How long the belt is. So if I go back underneath here, you're going to notice that they give us in equation 11.1. This is the overall length of the belt. Okay. Now, if I look at my belt, and I know I've got this underneath here, I'm going to zoom out as far as I can. My belt is continuous, okay? So you're going to notice that there is no break in this belt. But when we talk about the length of the belt, it is how long would I measure, if you would, around the circumference of this belt, okay? That's going to be how long the belt is. And as you can imagine, the longer the belt, the wider the center distance, okay? Now, to calculate that, we will use this equation right here. Okay, that is going to be the equation. Notice that the overall center distance that we're anticipating, as well as the diameters of the shiv that it has to fit over the top of, are going to be used to determine that length of that belt. Okay, and then once we know what the length of our belt is, then we can go back and we can specify an actual center distance. So the process that we go through design-wise, and we will see this in the second problem that we look at, we're gonna estimate a center distance so that we can determine about how long our belt is going to be. And then once we get an appropriate size length, which is listed here, the standard lengths are going to be listed here up on table 11.2, which is on page 305. Okay, so for the different categories of belt sizes, okay, there are going to be certain standard lengths, okay? Just like I said earlier when we were talking about gears, how many teeth are on a gear are going to be dependent on the category or the section that we're in here. So they don't make every single size belt. We're going to calculate a length based on an approximate center distance. And once we get that approximate length, we're going to go over and we're going to specify an actual length that we can get off the shelf. Okay, we want to go to Napa, for instance, and we want to walk in and say, here's the length of the belt that I need. Okay, and it's going to be one of these here in these categories. Once we get that actual length of the belt, it's probably not going to be the one that we calculated earlier. So now when we want to determine exactly how far apart the center distances are, because that's going to be crucial for your design. You have to accommodate this, right? You have to make sure that your design is going to have places where it's going to be able to fit this into my assembly. Okay. And then I'm going to have to go back and say, okay, what's the exact center distance based on a standard belt length? Okay. So that's really then our next one here is going to be the center distance. And you'll notice that it has these B variables here. And this B variable is just an intermittent equation using the length of the belt to just get that center distance equation at least a little bit shorter. Okay, that's all it is. So we're going to be calculating B and then inputting it up here to get our center distance. Okay. Then just below that, you're going to notice that we have two angles. These two angles are what we call angle of contact or angle of wrap. The angle of contact or angle of wrap is going to be how much of that belt is in contact with that sheave when it's actually running. Okay. And then it's going to be angle 1 on this side for the smaller sheave, and then angle 2 on the other side for the other sheave. Okay. All right. Let's go back to our PowerPoint presentation. We did angle of contact. We did those equations. Good. Now, belt kinematics. Belt kinematics is going to be those relationships that we saw in our gear module. And it's going to be things like the velocity ratio and also the belt speed. Okay. So let's look at the equations for velocity ratio and belt speed. Okay. So if we go up to the top of page 305, we're going to go like this. Okay. You're going to notice that we can calculate velocity ratio using the rotational speeds of the two gears, or I'm sorry, the two shifts. Remembering that the number 1 reference is going to be the faster rotating shaft, which is going to be like, if you would, the pinion or the input speed. And then the 2 is going to be the output or the slower moving sheave. Then you're going to notice that we have radiuses here. Radiuses are going to be the radius to the pitch diameter. So this is going to be the physical sizes. So 2 is going to be on the larger sheave and 1 is going to be the smaller. So notice that you have 2 on top here and 1 underneath. If you have diameters that you're dealing with, you could also use the diameters, and that's what they're showing down here. Okay, so we can set the velocity ratio equal to all 3 of those, and we can, if we know the velocity ratio and we need to determine something else, or if we know these and we want to determine the velocity ratio, any one of those are going to get us there. But the 2 most popular are going to be the pitch diameters or the rotational speeds. And again, 1 is going to be the driver or the faster moving shaft, and 2 is going to be the driven or the slower moving shaft. Okay. Now, belt speed. Belt speed is going to be the linear speed of the belt as it moves around. Okay. If we look at one of these shifts, okay, we know that if we rotate around and this goes and there's let's say a point along that belt that is on the sheave, and let's say it's not attached, and as it's going around, it is going to kind of go off of, or it's going to continue moving in a straight line as that belt goes around. That is representing how fast that belt is going along. So if there's a pebble, if you would, that is on the outside here, and when it gets here, it's going to fall off, but it's going to continue at a straight line velocity. That's what we're going to call the belt speed, because as it's here, it's going along with the belt, along with the belt, along with the belt, but then it can't make the corner. It's going to continue going. Does that make sense, everybody? Okay. So that straight line velocity on the outer edge of that sheave where the belt is, that's letting us know exactly how fast that is going. Okay. That is the same relationship that we saw on our gears and when we were looking at rotating elements in chapter 6 for straight line velocity on the edge of a link. Okay. And that relationship we're going to find is at the top of page 306. Now, there is a little bit of an error here. You'll notice here that it says belt speed is going to be equal to radius 1, okay, multiplied by the angular velocity of 1. So those two have to be together, okay? So if it's on the input, it has to be the input or the radius of the input multiplied by the rotational velocity of that sheave, okay? Or you can put them together here. The rotational speed of the output is going to then be the radius of the output, okay? If you know the pitch diameters, it would just be dividing that by 2. That's all that is expanding that out, okay? So this is the very same relationship we saw in module 6 when we talked about velocities, straight line velocities related to rotational velocity or rotational velocity of a link. And then here we're seeing that application on the outside or the edge of a sheave. And because the belt is, that's where the belt rides, this is also equal to the belt speed. Okay. Questions so far? It says here that the maximum, it says belts transfer maximum power at speeds of 4,000 to 5,000 feet per minute. It is best to operate within this range. If you're slower or much faster than that, you can be kind of on the outskirts of it, but you want to be somewhere right around 4,000 to 5,000 feet per minute for the best, performance of that belt. All right. Let's look at our first example, okay? So example 11.1, which is just below here on page 306. Let's go underneath, okay? And the problem statement, it says that we have a belt drive, okay? Kind of scooch this over, there we go. It's going to transmit power from an electric motor to a compressor of a refrigerated truck. The compressor must still operate when the truck is parked and the engine is not running. The 10 horsepower electric motor is rated at 3550 RPMs. Okay, so that's going to be our input speed, if you would. The motor sheave diameter is 5 inches. So they're telling us on the motor what size is that pulley or sheave that's going to be mounted. The compressor sheave is 7.5 inches in diameter. Determine the approximate or the appropriate industrial belt size and the operating speed of the compressor and the belt speed. Okay, so a couple things to go there. So what I want to do is we're going to start this by, okay, if we go back underneath, we want to just kind of start out at the top. I want you to kind of read through this again and let's make sure we know what we're given here, okay, in terms of information and give it the appropriate variables. And then we're going to look for what equations are going to help us with this and then just kind of identify the steps and use our book to help us with that. So as we look at this example, as I said earlier, it says that we have a 10 horsepower electric motor, and that's going to be driving or being the driver of this belt drive. And that is going to be at 3550 RPMs. So what that is going to be our angular velocity number 1, okay, or our driver. So I'm going to start with example 11.1. Oh, this is a practice problem that you'll be handing in, so make sure you're doing this along with me. And W1 is going to be 3550 RPMs. Okay, so if we're looking at our illustration that we were referring to earlier, that is going to be the W1 of our input RPM, or what we call our driver. This is going to be the faster moving shaft. Okay. There we go. Now it does tell us that the motor sheave diameter is 5 inches. Okay, so since this is the electric motor on the input, that means that when we look at this drive again, the diameter D1 is 5 inches. That's the pitch diameter of our shiv. So we're going to go here and we're going to say, okay, D1 is equal to 5 inches. Okay. So that's the shiv on that motor. Now the compressor shiv. So remember, we're going from that electric motor to the compressor on the refrigerated truck. This is our output side. This shiv is 7.5 inches in diameter. So if we look back over here, this side is our compressor side. Okay, so this is going to be a D2 of 7.5 inches. Okay, oopsie. All right. I think that's all the given information. Oh no, they also told us that our horsepower from that electric motor is 10 horsepower. So we just want to say capital P power is equal to 10 horsepower. Okay. So these are our given amounts from our problem. And now what they want us to do, they want us to determine the approximate belt size. So we want to find, what is our belt size? Okay. Belt size. We need to find the operating speed of the compressor. So we need to find W2. Okay. W2. And what is that belt speed? So that belt speed is VB. Okay. VB. Okay. Now, belt size is where we got to start because we have to first determine, okay, what is the size, that cross section? What V are we going to be? Okay. And remember that V, I'm going to go back a couple pages to page 303. We need to determine, are we a 3V, a 5V, or an 8V? Okay, what size are we based on the information? Now I'm going to turn the page here, okay? And we're going to use the chart at the top of page 304 to help us with this. Now, our faster shaft RPM of our driver, our electric motor, is 3550. And you'll notice that there's not a 3550, but there's a 4000. So I'm going to use that 4000, okay? I'm going to use that 4000. And then it told us in our problem that we had 10 horsepower. So what we're going to do is we're going to go over the 4,000 line here, okay? And we're going to go up the 10 line, okay? And they're going to meet right about there, okay? So as we can see, we land right in the 3V area. Now, we are at the top of this, but this would continue to go up, you know, even more. It's when you're close to a range of crossing over to a larger size. That's when, if you're really close to an edge, you'll want to go just to the other side, just to be a little bit more conservative, but we're well within our range here. So we're going to be a 3V belt, okay? So step number 1 is going to be from, what is this? Figure 11.4. Our belt size is equal to a 3V. Okay, belt size is equal to a 3V. And it's based on the RPMs of our faster shiv and the horsepower that's being transmitted, given in this problem. Okay, now you'll notice that in step number 1, they specified that very same 3V belt. Okay, so they agreed with us, okay, based on that information, which was clearly that. The next thing that the book says that they're going to do in this problem is we're going to calculate the driver shiv speed, okay? And this is going to be based on the velocity ratio that we have, okay? So what we're going to do is we're going to go back over to the velocity ratio, okay? The velocity ratio can be calculated. Actually, I'm going to look at 11.7 here. It can be calculated with the angular velocities as well as the diameters. Now, in the problem, we were given the diameter of the smaller shiv and the diameter of the larger shiv, right? So we have D1 and we have D2. So step number 2, okay, velocity ratio. We're going to find what the velocity ratio is based on those 2 diameters. So it's going to be diameter 2 divided by diameter 1. Okay, so diameter 2 is 7.5 inches and diameter 2 is 5 inches. Our inches cancel out, and I believe that's going to be 1.5, right? So our velocity ratio is 1.5, okay? Well, I shouldn't put a box around that. That's not a final answer. It's kind of an intermittent answer, okay? But we'll be using it. So I'm going to put a cloud around it. Okay. Now, it's asking us for we need to find what is I can check this one off. What is the output speed or the speed of the compressor shaft, right? So if I use that same relationship where I said, okay, our velocity ratio is also equal to W1 over W2, I now know my velocity ratio, right? Let's see, W2. And I know my W1, okay? So that's known. Then my only unknown is W2. So I can rearrange this to solve for W2, and that's going to be multiplying that up. So this will be W1 divided by that velocity ratio. Does that make sense? So this is just a rearrangement algebraically. So now I'm going to put those values in. I'm going to say 3550 RPMs divided by 1.5, right? So our angular velocity of our output, what do we get? Anybody get a number for this yet? 3550 divided by 1.5?
2,333.33.
Oops, I got 2366.666. Try again, Aiden, just be sure. 2 point, yep, Steve, I got the same as you, or, well, it's not 2 point, because remember, we're taking this number divided by 1.5. It should be 2,366.7 RPMs. Yep, forgot to care. And then Aiden, did you get that too? Okay, perfect. So this is one of our final answers, right? And I should actually put a box around this too. Okay. All right. So that's the angular velocity, how fast the compressor shaft is going. So if we look back at our illustration here, this is going around at 3550, and this is slowing down, and it's going at 2,367 RPMs. Okay. All right. So that means we got W2 done. Now, the last one we need to do is going to be the belt speed. We want to know how fast is that belt going. So if we look at, like I said, a pebble or a stone along here that's not affixed, if I would go around, this would continue in a straight line velocity. So this is our belt speed going to, if in this case, to the right when we are going in a clockwise direction on each one of our shifts. Okay, we want to know how fast is that. All right. So that relationship, if you remember, is going to be the belt speed VB is equal to the radius times the angular velocity of whichever shaft we're analyzing. I'm going to go with, well, we're going to go with number 1, only because we were given the angular velocity of our input off of that motor, and it's not calculated information, so we want to keep that to a minimum. And then we also know the diameter number 1, so we're simply going to divide that by 2 to get the radius and then multiply it by our W1. So step number 3 here is going to be belt speed, and that is our VB. We know that VB is going to be equal to the radius 1 times the angular velocity 1. Okay. Now, this is that same relationship that when we were in module 6, we learned that in and out of this equation, our angular velocity has to be in radians per second, right? Okay. So we need to convert our 3550 RPMs to radians per second. Okay. So I'm going to do that over on the side here. My W1 is 3550 revolutions per minute. 1 revolution, 2 pi radians, 1 minute, 60 seconds. Revolutions and minutes cancel. So my W1 you get 404.1. I don't know. I only did it once. No. I got a different number. Did you get 371? Or no?
Yeah.
371. Yeah. See, that's why we check it. So this is 371 point. What did you get?
7.5.
So 0.8. Okay. So we're good on this one, 371? Yeah. Joseph?
The thing doesn't say like R1 and W2. Not all that.
Oh, exactly. Yeah, that was something that we corrected. So, yep. So you want to put R1 and W1. You want to match them up, and then R2 and W2. Yeah, it was a misprint in the book. So whenever you're dealing with the radius, you want the radius to be on the shaft going at that RPM.
They really.
You know what? This book has been around. This is a good book. I like this book because I think they have good examples, good illustrations. But and this has gone through, I forget what edition is it. This is the 4th edition. I had it on the 1st edition. So many mistakes, and it's gotten better each time. It's gotten better each time, but yeah, there are a couple of things along the way here. Yeah. Okay. Yeah, so make sure we have R1 and W1, or if you choose the radius of your output, it's R2 and W2. Okay. All right. So now we can take our value and we can put it back in here. So this radius is going to be, it is on our input, so it's going to be 5-inch diameter divided by 2, okay, times 371.8 radians per second. Okay, so our belt speed, what do we get? You get 929.5 inches per second.
Yes. Correct.
Okay. Okay, Rainer got that. Okay, great. Aiden got it. So did Steve. Excellent. Okay, now if we look in the book, you're going to notice that they have the final answer in feet per minute, which is actually quite common for how you specify belt speed, okay, out in industry. Feet per minute is very common. So what we're going to do is we're just going to take our value and we're going to convert it. So go ahead and convert this value to feet per minute. And then we'll make sure that our answer matches. Yeah. And yes, indeed, we do match what they have as well. 4,647.5 feet per minute. You can put it in FPM like they do, feet per minute. That's totally fine, but I just have it feet and then per minute up, down. And that's going to be our final answer. So that is going to be the belt speed for this application. So process that we took here is we first started with specifying our belt. Okay. Then what we did was we determined what the velocity ratio was so that we could find what the output speed was for that second shiv. And then determining what the belt speed was for the two shivs that we had. And we came up with 4,647.5 feet per minute. Okay. Any questions on example 1? This is our first problem that you'll be handing in for your practice problems. Okay, so then what I'm going to do is I'm going to stop the recording here because we'll take our break and then we'll be back to do our second example.